All right, the bell work starts off and it says that if a sub n plus 4 is basically the term you're looking at. So I'm looking at a sub n plus 4 in my list. In English, what is a sub n plus 3, let alone Spanish, I guess? I'm just in words. What is a sub n plus 3 then? Liv?
The term before a sub n plus 4.
It's going to be the term before because it's one less. If n plus 4 is the one I'm looking at, n plus 3 must be a number 1 less. Like if my n was 2, 2 plus 4 would be, I'm looking at my 6th term, 2 plus 3 would be my 5th term. So a sub n plus 3 would be one term prior. Then what would a sub n plus 2 be then? If n plus 3 is one term prior, what is a sub n plus 2 then? Yeah, Grace. It'd be 2 terms prior. Yep. This would be 2 terms prior. All right, then it says I'm supposed to write 2 formulas for a sub n equals 7, 10, 13, 16, so on and so forth. So the first thing we need to check is it arithmetic? Because if it is, we know a nice little system to come up with our 2 equations. Well, 7 to 10 is plus 3. 10 to 13 is plus 3. 13 to 16 is plus 3. So this is, in fact, arithmetic. When it's arithmetic, I'm going to note my first term, and then I'm going to note my common difference. So my first term, a sub 1, is just 7. My common difference is a positive 3. As soon as we have those 2 things, we can make our 2 formulas. We have an explicit formula. Our explicit formula is going to be a sub n. It is going to equal my first term plus my common difference times n minus 1, which we could simplify down to 3n. 3 times negative 1 is negative 3. That would be plus 4. That is one formula. The other one we have to do is our recursive. Recursive always states your first term, which is 7. And then recursive is always a sub n equals a sub n minus 1 plus your common difference of 3. So those are my 2 equations, but that is exactly what you did for homework. So that being said, what questions do we have from our homework? So I hope that's why some of you had just blank ones here that you didn't understand it. Leo.
Number 4.
Yeah. Numero 4. We had 4. 3 over 2, negative 1, negative 7 over 2. These are the hardest arithmetic sequences to spot. Because at first it looks like, well, I have 4, 3 over 2. Those are tiny. I have negative 1. I have negative 7 over 2. I have dot, dot, dot. Now, arithmetic usually just jumps off because it's like adding 2, adding 2, adding 2, or subtracting 3, subtracting 3. You can't see this pattern unless you write it as a common denominator. And I'm looking at the 3 over 2 and negative 7 over 2. So my goal is to write all of them as fractions that have a denominator of 2. To rewrite 4 with a denominator of 2, I'd write 8 over 2. 3 over 2 is fine. Negative 1 I'm going to write as negative 2 over 2. And finally we have negative 7 over 2. Now we're going to be able to see an arithmetic sequence because the numerators are dropping by 5. That means I'm subtracting 5 over 2 over and over and over. So that's minus 5 over 2. That is minus 5. That's an ugly 5. That's a better 5 over 2. And that's a negative 5 over 2. So it's arithmetic where my first term is 4 and my common difference is negative 5 over 2. Is that far enough or do you want me to keep going? That's good? Okay. So that's why that one is in fact arithmetic. It's the hardest arithmetic one to see. Other questions at all? All right then. Today we're going to get into something called series, and which uses sigma notation. So let's first talk about what a series is. A series is the indicated sum of all of the terms in a sequence. So we talked about sequences already, like 2, 4, 6, 8, 10. A series is just adding all of those together. And we have two types of series. We have something called a finite series. A finite would be something like, let's say I had 2, 4, 6, and 8. Well, then we'd add them all together to make it a series, and we could actually come up with a total. 2 plus 4 is 6, plus 6 is 12, plus 8 is 20. Well, if finite is one type, the other type must be infinite. An infinite would be, an example would be 2 plus 4 plus 6 plus 8 plus 10 plus, and we would just keep going. We'd put a dot, 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 that you're just going to keep adding. Those you aren't going to come up with a total. There are some that do have a total, because some of these series will get really close to a number and we can actually get the total. But in this case, it just keeps getting bigger and bigger, so you'll never actually be able to get that sum. If you can find that sum, then you pass this class with an A+. But you have to find that sum. And infinity is not a number. All right. So that is, in essence, what a series is. It's a sequence being added up and getting the sum for it. One way to write a series is to actually go 2 plus 4 plus 6 plus 8 plus so on and so forth. But a way to reduce that writing, we use something using sigma notation. This is sigma. This is the Greek letter sigma. That is our shorthand for, hey, I'm going to keep adding something over and over and over. Now, what you see there is actually a very precise sequence and telling you exactly where to begin the sequence, where to end the sequence, and how to add it all together. So let's talk about some key components of this. First of all, you see that letter K? That letter K will not always be K, it's just a variable. This is called our index. Right here we have an equation. That equation is called your summand. So this 3K is called your summand. Basically what you're adding over and over and over. Now you can see we start at K equals 1, and then on top it tells you where you're going to stop. So it tells you where to start and it tells you where to stop. So that top and bottom numbers are your limits. So your sigma has three big things: a summand, which is your equation, index, which is your variable, and your limits, which tell you your start and stopping points. There is actually an answer to this. This is actually something that is being added up. So we're going to actually do the whole indicated operation right here. So our formula is 3 times k. It says start with k equaling 1. So we're going to plug a 1 in for that k. So we're going to have 3 times 1 to start off with. Then we're going to add. We're going to start at 1 and we're going to work our way up to 6. So now I'm done with 1. I'm going to replace that 1 with 2. So I'll have 3 times 2. So I replace the k with 2. Then I'm going to replace the k with 3. Then I'm going to replace the k with 4. Then I'm going to replace the k with 5. And finally, we'll replace the k with 6. And we stop there. So it says replace the k with 1 through 6, counting by 1. Now, if you wanted to, you could sum that all up and get an answer. We're going to do that right below. We're not going to waste the time on that one right now. But that's all the sigma notation says. It tells you what your formula is, what your starting variable would be, and where you end, 1 through 6. So this is just a sequence, 1 through 6. All right. Yeah, I covered all that. Let's do a couple examples. So first of all, your indexes should all be the same. They could be whatever you want them to be. You could pick J, you could pick smiley face, I don't care. But if you pick one down here, it has to be the same up here. If these do not match, you can't actually do the problem. It'd be like 3x equals y where z equals 4. The z equals 4 doesn't help you. So this one says k equals 1, so the indexes do match. So that means we are just going to replace k with 1 to start off with. So we'll have 1 squared. Then we're going to increase our index to 2. So my k value increases to 2, so I have 2 squared. Then my k value increases to 3, so I'll have 3 squared. And finally, my k increases to 4. I'll have 4 squared, and that's where I stop. I replace k with 1, 2, 3, and 4. That's where you stop. This is going to be 1 plus 4 plus 9 plus 16. That is going to equal 16 plus 9 would be 25 plus 5 is 30. 30 is what's called a partial sum. That means it had a starting point and an end point, and I could actually get the sum. I knew where it started and I knew where it ended. So that is called a partial sum. Our next one has a different notation. It says start with n equals 1, and then if you look at the top limit, it says infinity. That means you are not going to stop adding. You're going to add forever. We're not going to add forever. We're just going to put dot, dot, dot. But we'll put the first few to see what it looks like. So we are going to have 1 squared plus, then we move our index up 1. So it would be 2 squared plus 3 squared plus 4 squared and plus dot, dot, dot. In other words, we have 1 plus 4 plus 9 plus 16 plus dot, dot, dot. And we don't simplify that. We don't add those up and then go plus dot, dot, dot because we don't know what the sequence is then. So we leave the sequence open unless we could get to an actual sum. All right, most of the time we try to make these series, especially when we're writing them, we're going to write them soon on the next page. We're going to write our own. We usually try to start at like 1 or 0, but there are cases where it starts at another number. So if you look at that one, it says that our limits are 3 to 6. That means our very first I value is I, right? Yep, our very first I value is going to be 3. So we are going to say this equals 2 times 3 minus 1. I replace that I with 3. Then I replace it with 4, 5, and finally 6. So it tells me where to start at 3 and I end at 6. So our next thing will be plus 2 times 4 minus 1 plus, I'm going to run a room really quick. I should write it down below. I'm actually going to move it. Boop. Boop. Done. All right, then we're going to have plus 2 times 5 minus 1. And finally, we're going to have plus 2 times 6 minus 1. Well, 2 times 3 is 6, minus 1 is 5. Plus 2 times 4 is 8, minus 1 is 7. 2 times 5 minus 1 is going to be 9. Do we see a pattern developing? I have 5, 7, 9. What's my next one without even doing the math? 11. Sorry, Fritz. It's 11. What would the next one be if I said, make it up? It'd be 13. So if I said 3 to 7, our next one would be 13. 3 to 8, we would add 15. So doing that math, it is a partial sum, so we can actually do this. We'd have 20 plus 7 is 27 plus 5 is 30 dos. The last one's a weird case where you just kind of have to know what's going on. It says that my index is I, but the equation does not have I in it. It doesn't mean you can't do it. It just means you have to account for every single I. So we knew where to start and stop here. Because I said let I or k equal 1, I have 1 squared. Let k equal 2, 2 squared. Let k equal 3, 3 squared. Let k equal 4, 4 squared. We're actually going to do the exact same thing. We're going to let our I equal 1 to start off with. Well, if I equals 1 when we have a formula 4, we're just left with 4. The I has no impact on the equation. I'm left with just 4. I inserted 4 into the equation. It just doesn't have any effect on it. There's no place to plug it in. But I do have to account for the fact that I tried to plug it in. Basically, I'm trying to plug it in. It says, nope, I'm going to give you 4 back out. No matter what you plug in, you get 4 back out. So that's when I equals 1. Well, when I equals 2, it has no effect on the equation either. So we still have 4. When I equals 3, it has no effect on the equation. You still have 4. When I equals 4, it's still just plus 4. And finally, when I equals 5, it just equals 4. You are plugging I in. There's just no place to do it, so it doesn't change it. It is just 4, 4, 4, 4, 4. 4, 4, 4, 4, 4 is a sequence. It just has a common difference of 0. It doesn't move. You know what the next number would be. It's a sequence. But you do have to add it all up. So it is going to be 4 times 5, which is going to be 20. So in this case, you just have to count how many terms there are and do that multiplication. That is when you don't actually have an index in your equation. It is telling you to add 4 over and over and over until you get to the end of your loop. All right, questions on any one of those 4 or what I'm doing with those? Big thing is just know where your bottom limit is and where your top is. Where do I start and where do they end? And I always count by ones. All right, surely if we can go one direction, if I can give you a summation, you should be able to spit out a sequence. And likewise, if I give you a sequence, you should be able to come up with the summation for it. That's what we're supposed to do here. It says write each series using summation notation. When I ask you to do summation formation, the hardest part you're going to have to do is coming up with the equation. This equation here. The easiest way to do that is don't treat it as a summation. The very first thing I want you to look at is look at the sequence first. So whenever I have you go from numbers like this adding to summation notation, your first thing should be look at the sequence first. So I'm going to forget about the pluses. I'm just going to look at the numbers. So this is my sequence is 2, 4, 6, 8, 10. I do want to reiterate that I say things that you should be writing down that I'm not might necessarily not write down on here. All right, so we have 2, 4, 6, 8, 10. Well, if we look at this, this is just a sequence where we're adding 2 over and over and over again. Whenever you're adding the same number, it is arithmetic. And with arithmetic sequences, we just need to know our first term, a sub 1 equals 2, and our common difference, or d, is going to be 2. There's only one type of equation that works for this. You cannot use recursive. You cannot use recursive. It has to be when I plug 1 in, I know what value comes out. When I plug 2 in, I know what value comes out. So you have to write an explicit formula. Once again, this has to be an explicit formula. So that's what I'm going to write here. And my explicit formula would be a sub n equals my first term plus d times n minus 1, which I am going to reduce. I'm going to multiply the 2 by everything, so I'll have 2n. I have 2 times negative 1, which is negative 2 plus 2 is 0. So that is just 2n. That's why sometimes it's just nice to simplify stuff, because now we just have 2n. The hard work is over. Now all we have to do is write our sigma notation, which is our big E, and we're going to put that explicit formula there. Now I just need a lower limit to an upper limit. When I'm writing this by myself, you should always have your n equals 1 as being your lower limit, because I want my first term to be 1. When I plug a 1 in, I should get this number out. So this is my n equals 1. 2, 3, 4, 5. Brody, can you look up? Yeah. Thanks. So this is going to be 1, 2, 5. My fifth term is supposed to be 10. When I plug 5 in, I have 2 times 5, which does equal 10. This is my summation formula. Once again, the hard part is just coming up with this equation. Everything else should just be starting term is 1 and however many terms you have. If I had 10 terms, it'd be 1 to 10. That is just the beauty of being able to write it yourself. You made it, so you start at 1 and you go to wherever we're going to go. All right, our next one is probably one of the more difficult ones you're going to have to deal with. And that is because we have to deal with it in parts. So, first of all, with an arithmetic sequence, we are not concerned with the fact that it's going positive 1/5, negative 1/7, positive 1/9, negative 1/11. Because with an arithmetic sequence, we can take care of that by doing that negative 1 to the n minus 1 or negative 1 to the n. That will tackle going from 1 or 1/5 to a negative 1/7 to a positive to a negative to a positive to a negative. So this only works in arithmetic sequences, but in arithmetic sequences, to alternate between positive and negative, we are going to use, does anyone want to tell me what we're going to use? We have 2 choices. Negative 1 to the n or negative 1 to the n minus 1. What would I use in this case? You got a 50-50 shot. I only picked 2 of them. Rena?
Is it n minus 1, negative 1?
It would be n minus 1. Yes, it would be n minus 1 because our first term should be positive. So when I plug a 1 in here, I better get a positive out. 1 minus 1 is 0, negative 1 to the 0th, that would give me a positive out. So that is in fact the one we're going to use. Once again, I say things, and a lot of people don't write stuff down. This only works for their arithmetic sequences. Now I do not care about the positive negatives. Now I only care about the 1/5, the 1/7, the 1/9, the 1/11, and the 1/13. We really can't create a common denominator. If we try to use 13 or something, it's going to get enormously big really, really quick. So it's probably not going to be arithmetic totally. But if for a second you forget about the ones on top, it goes 5, 7, 9, 11, 13. It goes 5, 7, 9, 11, 13. That is arithmetic. That is arithmetic where my first term equals 5 and my common difference is 2. It goes 5, 7, 9, 11, 13. I just keep adding 2. So the explicit formula for just the denominator would be a sub n equals my first term plus my common difference times n minus 1, which I could simplify down to 2n. 2 times negative 1 is negative 2, plus 5 is 3. So we had to tackle this one in parts. First, I had to deal with the positive and negative. There is no way for an arithmetic sequence to go positive, then negative, then negative. The only way it can be tackled is by using this, because there is no common thing you can add that will make it positive and then negative, positive, then negative. Then we had to recognize that you can't just keep adding fractions to get there, so I just have the denominator. You can always do that if your numerator is always the same. My numerator is fixed at 1. It is always going to be 1. So the equation I'm going to come up with is 1 over something. We'll come up with all of those. So let's come up with our equation for our actual thing. So this was just a little scratch work. This was just to take care of my denominator. Let's take care of the entire problem. Let's call it a sub k. A sub k is going to take this alternating positive, negative, and I'm going to throw it out front. That will take care of my alternating positives and negatives. So I'll negative 1 to the n minus 1. My numerator is always going to be 1. So I'll have a 1 on top. My denominator is the only thing that's changing, so I'll put that 2n plus 3 on the bottom. This should handle every possible one up there. I've got my alternating negative and positive. I have a 1 for a numerator, and I'm taking care of this 5, 7, 9, 11, 13. Let's check to make sure it works. Let's check it with our third term. Our third term should be a positive 1 over 9. Well, negative 1 to the 3 minus 1 is negative 1 squared. That's positive. That's good. When I plug 3 in here, I have 2 times 3 is 6, plus 3 is 9. We're good. It'll work for all of them. So there are times where our arithmetic sequence is just buried in a denominator, or it's buried in a numerator or something. So you can break things apart and put it back together like this. Like I said, that's the hardest part. Now we just have to write it as a summation. I'm going to move that negative 1 to the top, so I'll have negative 1 to the n minus 1, all over 2n plus 3. I really messed up here. All of those n's should actually be k's, because I did say a sub k. So I should probably stick with that. So let's make them k minus 1, 2k plus 3, and we'll have 2k plus 3 on the bottom. This would be k minus 1. Not a big deal. It's just a small notational thing. All right, so now we're going to start with k equals 1. And how many terms do I need? I need 1, 2, 3, 4, 5. So I end on term 5. So k equals 1 all the way to when k equals 5. That is my finished answer. Now, this is a really hard sequence to write out. If you understood everything I did, awesome. If you can replicate it, awesome. We will have a problem like this on the test. I guarantee it. It's been on there every single year. It is the best arithmetic problem because it alternates between positive and negatives, and it's not an entire arithmetic. It's just in the denominator. It's a really good problem to have. All right, the last one is not arithmetic either. The whole thing isn't arithmetic. In fact, none of it's arithmetic. In fact, you have to recognize the numerator is staying the same, but the denominator is changing. So this is one of the times where you're just going to have a 1 on top, just like we have here. And taking that in mind, think of that 1 as actually being 1 over 1. So every one of our problems is going to be 1 over something. I just need to come up with what that something is. Well, we have 1 over 1, 1 over 4, 1 over 9, 1 over 16. Those are all perfect squares. So instead of picturing this as 1 over 1, I'm thinking it is 1 squared. 4 is 2 squared. 9 is 3 squared. 16 is 4 squared. So that means my explicit formula is going to be 1 over something. Something squared, because they're all squared. You just got to figure out where it's being squared, i.e., my first term should be 1 squared. So when I plug 1 in, I should have 1 squared. When I plug 2 in, I should have 2 squared, 3, 3 squared, 4, 4 squared. So that's just whatever term I'm at, I'm just going to square it. My first term is going to be 1 squared, 2 is going to be 2 squared, 3 is going to be 3 squared. Once again, that's your hardest part, because now we just write our summation by doing our explicit formula. We'll start at n equals 1, and we're going to notice it does say dot, dot, dot. So that means it's going to keep going on forever. So that's the time where we bring out our infinity symbol, n to infinity. All right, so that's writing it. Now we're going to get to something that's confusing at first, but if you can get a handle on it, or you ask questions, it really isn't that bad. And that is something called changing the index. Changing the index. And this will be a lot more helpful if you understand this when you get to calculus, because you're going to add summations to each other. In order to add summations to each other, they must start and end at the same place. That generally means we don't want things to start at 2. We generally move everything so it starts at 1. That is called changing the index. Rather than starting at 2, I want it to start at 1, but I want the summation to still be the same. I can't just change that to 1 and you're done. No, because then you're just going 1 through 6 and you're adding 1 through 6 instead of 2 through 6. So you can't just say I'm going to put it as 1. A lot of things happen to keep it still balanced. All right, so we are going to rewrite this series with an index of k. So we're going to change that I to a k. And k is going to start at 1. Let's just start off by what it's going to look like. So what they're asking me to do is write the same thing, but I'm going to write k equals 1 here in place of that I equals 2. So we need to go from 2 to 1. That is called adjusting down. I am adjusting down 1. I start at 2, I adjust down, which makes it 1 lower. When I'm adjusting down, what I'm kind of looking at is I need to subtract. To get from here to here, I need to subtract 1 from it. To get from 2 to 1, not a big concept, I subtract 1 from it. The big concept is that basically k equals I minus 1. Because when I plug a 2 in here, I get my 1 back out. Well, since this is true, what else is true is the fact that I can just move this 1 to the other side and say, well, that means that I equals k plus 1. So I'm adjusting down by 1, so I have to subtract every I by 1, which means that I actually equals k plus 1. Let's check to make sure that works. If I replace this I with k plus 1, I'll have k plus 1 equals 2. Subtract both sides by 1, and I end up with k equals 1. But this is still the same I. So I'm going to replace this I also with k plus 1. So this is going to be k plus 1. Now, since I adjusted this down by 1, I need to adjust the 6 by 1 to make it 5. So we can do it this way every single time, or you can listen to what I'm saying and you can do it just understanding a pattern. When I adjust down from 2 to 1, I increase every one of my I values by 1 by replacing with k plus 1. If I would adjust down by 2, I would change this to k plus 2. So what's basically happening is as I adjust down, I need to keep it balanced by pushing up the other side. So as I adjust down, I keep adding 1, 2, 3, 4, 5 to that one. That means if I need to adjust up, let's say I'm going to turn this 2 to a 5. That means I'd be adding 3. That's adjusting up. That means that I would actually subtract 3 from all my I values, so I would replace that with k minus 3. That's one way to look at it, or you can look at it this way. It's a tough concept to tackle at first, but when you start doing it, it kind of makes sense that you adjust. Now let's make sure that this is still balanced. If we look at this one would be 2 plus 3 plus 4 plus 5 plus 6. Do we all understand that with this summation here? This one would be 1 plus 1, which would be 2. 2 plus 1, which would be 3, 4, 5, 6. It'd be the exact same sum for both of them. So make sure you do that check after you did that. This is 100% correct. All right, let's do some examples. We'll do it one way, then we'll do it the other way. All right. So first of all, let's write what it's going to look like. it's going to look like where we're going to have k equals 1. So now what I'm thinking right now is this is adjusting down 2. So that's one way to look at it. If I'm adjusting down 2, that means I'm going to add 2 to every one of my i's. So instead of I, I'm going to have k plus 2i. That's that adjusting up and down if you keep it balanced. If you don't want to do it that way, you can always go back to the fact that, well, if I equals 3 and I need to make k equaling 1, that means that k must equal, well, to get from 3 to 1, I have to subtract 2. So that means I minus 2. I'm going down 2. Well, that means for every I, so this leads me to the fact that I equals k plus 2, because I'm just adding 2 to both sides. Nothing magic's happening here. I'm just adding 2 to both sides, and now I equals k plus 2. So this is that balancing act. As this one goes down, we add to their side, and the other side goes up. So now I'm going to replace all of my i's with k plus 2. So we're going to have 1 over k plus 2 squared. Infinity is not affected by adjustment. There's no such thing as infinity minus 2. Since infinity isn't even a number, it's a concept. So you're going to leave it as infinity. But realistically, that is infinity minus 2, but put a drop in the ocean, you're not going to see a difference, right? So you're not going to see a difference on that one. All right, the last one. What it's going to look like on the end is I'm going to have to make this equaling k equals 1. I am going up by 2, so that means that my i's are going to both of them are going to go down 2. So really it's going to become k minus 2. But the actual algebra behind it is, well, to get from 1 to negative 1, I have to do k equals I plus 2. I need to go from that negative 1 to 1, so I'm going to have I plus 2. Well, that leads me to the fact that if I subtract 2 from both sides, I'm going to have I equals k minus 2, k minus 2. So now we're going to replace both of our i's with k minus 2. So in the top we have negative 1 to the I, but that's going to be negative 1 to the k minus 2. And down below we're going to have 2 times k minus 2 plus 1. We're also going to note we are increasing our I values by 2, so instead of going to 5, we are now going to go to 7. You should simplify that denominator, but we are right at that time. Remember, this homework is due tomorrow, whether we have school or not. It should be done for tomorrow. If we do not have school tomorrow, your homework is to watch the video, do the lesson, and the next day will be work time. All right, guys, have a wonderful day. If I don't see you, I'll see you when I see you. Stay warm. You're welcome.